Good afternoon. I'm Dr. Lainey Rutko, and I'm delighted to welcome you to this installment of the Johns Hopkins Congressional Briefing. In this series, Johns Hopkins experts provide a briefing on major policy topic, and we offer Q&A in real time. The goal is to provide policymakers, their staffs, and members of the public with up-to-the-minute insights and analysis from Johns Hopkins experts. In today's briefing, our panel will discuss some of the latest developments in civilian space exploration, discovery, and research. This is an opportune time to discuss these topics because, as many of you are aware, in recent months, we have witnessed impressive advances, such as the launches of both the Double Asteroid Redirection Test, or DART mission, and the James Webb Space Telescope. In 2021, the Parker Solar Probe flew through the sun's upper atmosphere, becoming the first spacecraft to do so. We are also treated to exquisite close-up pictures of Mars and other planets and moons in our solar system, where we have robotic probes. I'm delighted to introduce the moderator for today's briefing, Dr. Chuck Bennett. He is a Bloomberg Distinguished Professor, Alumni Centennial Professor, and a Johns Hopkins University Gilman Scholar in the William H. Miller III Department of Physics and Astronomy, with a joint appointment at the Johns Hopkins Applied Physics Laboratory. A member of the National Academy of Sciences, Dr. Bennett is a distinguished researcher in cosmology, a recipient of NASA's Outstanding Leadership Award, a two-time recipient of NASA's Exceptional Scientific Achievement Medal, and an awardee of the Breakthrough Prize in Fundamental Physics. He led the WMAP space mission, which precisely quantified key properties of the universe. Dr. Bennett directs Space at Hopkins, which connects Johns Hopkins researchers across the university with one another, students, the media, and government officials. Dr. Bennett, allow me to hand today's briefing over to you.
Well, thank you very much, Dr. Rutko. In 1957, the Soviet Union launched Sputnik, which shocked America. In response, the U.S. committed itself to the enormous technical challenge of sending astronauts to the moon and back safely to Earth. Since then, the U.S. space program has continued to demonstrate increasing scientific and technological prowess. Both humans and robots now explore our solar system, and telescopes explore out to the limits of our universe. These teach us about our place in the universe, and they inspire us. We also confront threats to life on Earth by predicting space weather and working towards planetary defense from potential Earth-impacting objects. Many of these efforts are now international, and we can no longer assume that the US will lead the world in every area as we used to do. Johns Hopkins University is unique. The Applied Physics Laboratory, a space center, is part of Johns Hopkins. We house the Space Telescope Science Institute, which is now focused on the James Webb Space Telescope. We also have a leading medical school, which with interests in both using space to improve human health here on Earth and to understand space effects on astronauts. We have leading planetary scientists, astrophysicists, engineers, users of space data systems, etc. All of this is united by Space at Hopkins. For today's briefing, I'm joined by three of my colleagues. Dr. Jason Kalirai is the Mission Area Executive for Civil Space at the Johns Hopkins University Applied Physics Lab. Jason oversees APL's work to design, build, and operate NASA and international missions that are solving decades-long challenges in space exploration. He also oversees APL's Space Science Research Program, technology development programs, and operation of spacecraft and science instruments. Today, Jason will talk about space weather and planetary defense, including discussing the Parker Solar Probe and the Double Asteroid Redirection Test, or DART, mission. Dr. Adam Riess is a Bloomberg Distinguished Professor, the Thomas J. Barber Professor in Space Studies at Johns Hopkins, with a joint appointment with the Space Telescope Science Institute. He is an astronomer and a member of the National Academy of Sciences. Adam's observations of the accelerating expansion of the universe earned him the 2011 Nobel Prize in Physics. Adam will discuss the significance of the James Webb Space Telescope. Dr. Sabine Stanley is a Bloomberg Distinguished Professor at Johns Hopkins, where she is chair of the Morton K. Blaustein Department of Earth and Planetary Sciences, with a joint appointment in the space exploration sector at APL. Sabine is a planetary physicist focusing on magnetic fields as a means of studying the interiors of planets, and she leads the Magnetism and Planetary Interiors Research Group. Today, Sabine will provide an overview of recent developments in planetary science and talk about several important space missions. Now, before I turn to each of our panelists for their remarks, I want to remind you that we'll be providing answers to your questions in real time. So please submit questions for our experts in the box at the bottom of your screen. Beginning with Jason, each of our panelists will provide a brief overview of key topics. Jason, would you please update us on some of the Applied Physics Lab's exciting work related to space weather and planetary defense?
Yes, thank you very much, Dr. Bennett, and good afternoon, everyone, and thank you for the nice introduction. I've been passionate about space exploration since I was a young kid growing up in a small town with dark skies, and the passion has stayed with me through my education, my doctorate in astrophysics, a decade leading research teams, and now working hand in hand with NASA to advance our nation's boldest space exploration programs. And the opportunity space for U.S. leadership and collaboration with the international community to explore new dimensions of space exploration could not be greater. So as Dr. Bennett said, I'd like to focus my remarks today on two emerging space-related threats that our nation and the world face. First, I want to talk about space weather. So to introduce this topic, let's put our sun into a broader context. Our sun is the lifeblood and heartbeat of our solar system. It is 99.8% of our solar system's mass. It's so large you could fit 1 million planet Earths inside the volume of the sun. And the energy generation from the sun is equivalent to billions of hydrogen bombs going off every second for billions of years. So as a result, our home planet Earth is at the mercy of what the sun decides to do. So this video illustrates the first space threat, space weather. Often we think of space being empty. It's not. Space is teeming with combinations of neutral and charged particles, most of which originate in stars. And space weather refers to the radiation, plasma, the energetic particles that are flowing out from the sun. And while there's a steady state of radiation in all directions, it can also occasionally be channeled and amplified into a specific direction. And some of those directions, unfortunately, can intersect planet Earth. And so these events include solar flares and coronal mass ejections, where millions of tons of solar plasma can be shot out of the sun, hurled through space at thousands of kilometers per second. And we've seen these impacts before. In 1859, there was a Carrington event that knocked out telegraph lines across the Atlantic. 30 years ago, there was a solar storm that knocked out the power grid across the Eastern Canada and US. And just a decade ago, in July 2012, a superstorm just missed planet Earth as it was orbiting the sun. If it had hit, we would still be picking up the pieces today. So these solar storms are even more dangerous today than in the past years due to two reasons. First, our sun has an 11-year cycle in its magnetic field. It came out of its solar minimum recently in 2019, and it'll be at its peak magnetic outbursts and turn violent in just a few years. Second, there's been a proliferation of space by satellites, as you can see in this video. 30 years ago, we had 500 satellites in space. 10 years ago, we had 1,000 satellites in space. 10 years from now, we'll have 100,000 satellites in space. And so a massive solar storm today would not only create widespread damage on Earth, including communication systems, infrastructure failures, power grids, but it could also be catastrophic to our space industry, including our civilian and national security assets. So to try and help prevent this from happening, Johns Hopkins APL just developed a space weather gap analysis report. So let's cue up the next slide. This is a 150-page report with a nice high-level executive summary, a brochure that outlines the steps our nation needs to take to bring space weather predictions into the same era as terrestrial weather predictions are today. This report is a deliverable to NASA's Heliophysics division, and it advocates for a suite of new instruments, measurements, and missions across multiple destinations in the solar system and the Sun-Earth system to allow forecasting of space weather. This includes both new assets and replacing older assets that are nearing the end of their life and or are technologically outdated. So I encourage everyone to download this 15-page brochure and look forward to an expansion of our space weather capabilities due to this critical threat. Related to space weather, Dr. Bennett mentioned that Johns Hopkins APL developed a bold NASA space science mission called Parker Solar Probe. We launched it in August 2018, and the spacecraft quickly became the fastest human-made object ever built, as well as the closest to approach the sun. Today we typically study the sun from Earth at a distance of 93 million miles. Using an innovative mission design and cutting-edge technologies, Parker has now flown within 5.5 million miles of the sun. In fact, the spacecraft just crossed the critical transition region separating where the solar wind originates and where the outer atmosphere of the sun ends. So we have flown a spacecraft through the outer atmosphere of the sun. More than 600 scientific research papers have already been published from Parker to understand solar phenomena such as space weather at its source location. And over the next few years, we're going to continue to dive in closer to the sun and eventually reach 3.8 million miles. This is incredibly close. For example, right? Consider the sun is 1 million miles across, almost 1 million miles across. So the second space threat I want to briefly talk about today is planetary defense. So let's cue up the last slide. Planetary defense refers to the threat that Earth faces from asteroids that could impact our planet, our cities, our people. As you know, it was an asteroid that wiped out the dinosaurs millions of years ago. Just a decade ago, a giant asteroid exploded over a city in Russia called Chelyabinsk and released 20 times as much energy as a World War II atomic bomb. It created major disruptions, economic losses, and casualties. These asteroids, especially smaller ones, are peppering Earth all the time. Every 2 weeks, we're hit by an asteroid that's a meter across. It is inevitable that a giant asteroid will impact Earth in the future. If it impacts over a major city, the losses could be catastrophic. Let's do something about it. Image that you see is a picture of NASA's DART mission, the Double Asteroid Redirection Test. This is NASA's first planetary defense mission designed to demonstrate the kinetic impact technology to move an asteroid in space. Johns Hopkins APL designed, built, and tested the DART mission for NASA, and we launched it from Vandenberg Space Force Base just 2 months ago in November 2021. DART is currently headed towards a small asteroid called Didymos. It's a 160-meter, small asteroid called Dimorphos. It's a 160-meter across asteroid. It's actually a moon to a larger asteroid called Didymos, and the small asteroid takes about 12 hours to go around the big moon. This binary asteroid system is not a threat to Earth. It's the perfect test case for this experiment. DART will collide with Dimorphos, the smaller moon, traveling 14,000 miles per hour and autonomously course-correcting its trajectory in the hours and minutes before impact. On September 26, 2022, September 26 of this year, at 7:15 p.m. Eastern, for the first time, humanity will have moved an asteroid in space. This target binary system was intentionally selected due to its proximity to Earth and the binary nature that allows us to precisely measure the deflection of Dimorphos by simply measuring the new orbit of the system after impact. We're expecting the orbit to change by 10 minutes as a result of the momentum transfer. So this is an incredibly exciting project that has taken something that was in the realm of science fiction and brought it into our reality. It's captivated a huge public interest due to the change in how people view our planet. The experiment is also scalable in multiple dimensions. We need to test additional technologies in the future, and this can all be done by building a robust planetary defense program at NASA to prevent the second kind of space threat from harming our precious planet and our civilization. So again, thank you to everyone for attending. I look forward to your questions and discussions after my colleagues speak. Dr. Bennett, back to you.
Thanks very much, Jason, and thank you for updating us on this very important work. Again, as Jason just said, I'll remind you to enter your questions, and we'll try to get to as many as we can after the presentations. Dr. Adam Riess, on Christmas Day, as you may remember, the James Webb Space Telescope was launched on an Ariane 5 rocket from French Guiana. Can you offer us some thoughts on the importance and the promise of the Webb Space Telescope?
Sure. Thank you for joining us. I must say, as an astrophysicist, every day feels like Christmas these days. There's never been, I think, a more exciting time to study space and the universe than in the present year. And what we have to thank for that is a process that we call the decadal survey in astronomy and astrophysics. And we're now beginning to enjoy the fruits of that. The decadal survey is a survey undertaken every decade by our community where experts gather together and figure out what the priorities really need to be. This is a process that is facilitated by the National Academy for Sciences. It's done at the request of the federal agencies. And so the missions I'm going to talk about are the result of those past processes. It's really the envy of most science communities. Before I talk about the James Webb Space Telescope, let me just give a short advertisement for another mission that's coming along in about 5 years that was requested by the 2010 Decadal Survey, and that's the Nancy Grace Roman Telescope. The Nancy Grace Roman Telescope is a wide-angle near-infrared mission, a very interesting story. It has a mirror the same size as Hubble, and the mirror and base facility actually came secondhand from the National Reconnaissance Office, but was repurposed for this mission, which will study exoplanets, dark energy, and general astrophysics, and that should launch in about 2027. Meanwhile, of course, what's really been in the news and is just incredibly exciting is the flagship of all flagships, really, for NASA, the James Webb Space Telescope, which was selected in the 2000 Decadal Survey. This is more than 20 years in development. This is an extremely advanced, extremely capable telescope. It's 6.6 meters across compared to Hubble, which was 2.4 meters. If I could see the first slide, please. And so this telescope operates in the near infrared. It uses very advanced technology. In particular, it's folded up almost like origami and then is unfolded. 18 individual segments of gold-coated beryllium are brought together to produce the one very large aperture. There's wavefront sensing, which will be used to focus and coordinate these individual mirrors in space. This is done with 7 individual actuators per mirror that will bend and sculpt each of the mirror segments to produce what is essentially a perfect image once this telescope is on orbit. The goal of this telescope, like most telescopes, is to see fainter and farther and to see in high definition, in this case, in the infrared. How will we do that? Well, one of the key elements to be able to see very faint things is to not see the noise or what we call the background of the telescope itself. And so it's critical for this telescope to be extremely cold. We will be operating it at 50 degrees above absolute zero. That's minus 370 degrees Fahrenheit. And the way we get it so cold, first of all, is to park it very far from Earth, away from the heat of the Earth. It's at a location called Lagrange Point 2, which is 1 million miles from the Earth, 4 times the Earth-Moon distance, where it will sit in its own shade. It has its own sunshade, like a giant parasol the size of a tennis court. Will keep it nice and cold, plus it will have active cooling on it that will help bring it down to its final cold temperature, at which point we will align and calibrate the telescope. As I said, it's much more powerful than Hubble. It has 5 times the area in its mirror, and its instruments are much more sensitive. So overall, I would say it will be about 100 times more sensitive than the Hubble Space Telescope. If I could see the second slide, this telescope will be operated at the Space Telescope Science Institute, which is on the campus of Johns Hopkins University. And this will really be the nerve center where we run the science program. We calibrate the telescope. We also get applications to use the telescope and deliver the data to the community. And so what will we do with this telescope? Well, pretty much everything. Like the Hubble Space Telescope, it will address almost every area of astronomy and astrophysics, including many surprises that we can't anticipate yet. However, I'll mention just a couple of things that are particularly exciting. If I could see the third slide. In our understanding of the universe, we have a really cosmic chicken and egg problem. What came first in our case, what came first, stars or galaxies, which were the first things to coalesce and become what we know them to be today shortly after the Big Bang? Did stars first turn on and coalesce into galaxies, or did galaxies form of dust and gas and stars form inside of them? And so with this telescope, we will look back to about 99% of the way to the Big Bang, about 100 million years after the universe began, and look and see which objects appeared first. We will be able to do that by seeing in really high resolution, as you see on the image on the right, showing you what a galaxy would look like without this telescope and then with this telescope. Another very exciting application of this telescope, if I can have the next slide, is to begin to do some reconnaissance of the composition, the chemical composition of atmospheres in exoplanets. Exoplanets are planets that orbit other stars, and we will begin to ascertain whether they have the molecules we think are necessary for life, for them to be habitable. So we will take spectra as those planets pass in front of their home stars and learn whether there is oxygen, carbon dioxide, water, methane, things like that. So that will be extremely exciting. And finally, I look forward to following up on some of the mysteries left to us from the Hubble Space Telescope. One of the ones that I've been most interested in is why it looks like the universe is expanding faster than we expected it to be, even based on all of the understanding that we currently have. So I'll just briefly tell you the status of the telescope. The first 30 days were extremely exciting. They were often called the 30 days of terror as the telescope launched and all of these complex components unfolded, deployed, and all of that worked extremely well. And in fact, those 30 days are over now with the telescope now fully deployed at its home, parked at Lagrange Point 2 in an orbit around that location. Now, over the next several months, we will continue to cool the telescope down to reach its operating temperature, and also right now begin focusing the telescope. We will observe bright stars and use those and the wavefront sensing to distort those individual segments and produce that perfect focus of the telescope, calibrate the various images and capabilities, and we hope about by June to be able to begin science observations. There will be early release observations, probably the end of June or perhaps by the 4th of July. And then after that, we will start the year one program of selected science. And so this is an extremely exciting time. Myself personally, and with my research team, we were awarded 24 hours in the first year. And so we can't wait to get going. And with that, I will turn back to Dr. Bennett.
Thank you, Dr. Riess, and thank you for describing what I think was an example of technological prowess involved in designing and building, testing this telescope. And I personally cannot wait to see those results coming in. That's fabulous. Dr. Sabine Stanley, I'd be grateful if you could provide us with a brief overview of recent developments in planetary science and talk about some of the significant space missions that are currently underway and forthcoming.
Great. Yeah, thanks, Dr. Bennett, and thanks to everyone who's joined us today. So I'm going to highlight some current and upcoming spacecraft missions to planetary bodies and really try to explain why the work is so important for us to really understand how Earth itself works and how life can thrive here. And I'm going to start with the Mars InSight mission. So if we can bring up the first image. InSight's the first mission that actually put a seismometer on another planet. It's been collecting data from Mars quakes. So those are earthquakes on Mars, okay? And those Mars quakes create seismic waves that travel through the planet and probe the structure and composition of the interior. Now, the seismometer is under that white dome in the animation you see there. Over the past 3 years, we've detected over 1,200 Mars quakes, and we've learned about all the layers inside Mars, like the crust, the rocky mantle, and the core. We've also learned about the consistency and the structural integrity of the surface under the lander. And this is all stuff one would want to know for future human exploration of Mars. Now, lately, the mission's been trying to remove some of the noise in the seismic data so that we can see even more Mars quakes. And one source of noise comes from the wind that moves over that cable that's joining the seismometer to the spacecraft that you see here. So what we're doing is we're burying the cable under the Martian sand thereby shielding it from the wind. Now, nothing like this has ever been tried before on Mars, and it's amazing to see the ingenuity of the engineers and scientists on this mission. So now let's shift to another mission, the Europa Clipper mission. So if we can bring up the second image, great. So the expected launch date for this mission is October of 2024, so about a year and a half-ish from now. And the spacecraft, actually 2 years and a half-ish from now, and the spacecraft will go to one of Jupiter's most fascinating moons. It's named Europa. Okay, Europa is tiny. It's a bit smaller than Earth's moon, and the surface is covered in an ice shell that's about 10 miles thick. But there's strong evidence that underneath that ice is an ocean with about twice as much water as all of Earth's oceans combined. So finding a planetary body with liquid water is exciting because water is essential to the complex chemistry that makes life possible on Earth. What's also exciting, and you can see in this picture, is that the surface of Europa is covered in cracks. So the ice on the surface shifts around, creating these cracks. And we have evidence that plumes of water from that ocean underneath are escaping outwards from the cracks. So that means we might not actually have to dig beneath the ice shell to study the ocean. The ocean may actually come to us through those plumes. The Europa Clipper mission's main goal is to investigate whether Europa has the capability to support life. So Europa also has other ingredients that are necessary for life as we know it. So for example, below the ocean is a rocky interior, and chemical reactions at that water-rock interface can allow more complex organic molecules to form, which end up being the building blocks of life here on Earth. Life also needs energy to grow, and Europa may have that as well in the form of hydrothermal vents at that rocky seafloor. So next I'll talk about the Dragonfly mission to Saturn's moon Titan. Quick intro to Titan. There are only 2 planetary bodies in the solar system that have a dense nitrogen-dominated atmosphere. One is Earth, one is Titan. There are only 2 places in the solar system where liquids are stable and form lakes and rivers on the surface. One is Earth, one is Titan. The lakes on Titan are actually made of liquid hydrocarbons, things like methane and ethane, but there's evidence that there is a water ocean under the surface of Titan, and things like meteor impacts and cryovolcanoes may bring that ocean water to the surface. So the Dragonfly spacecraft is a dual quadcopter. So basically it has 8 spinning helicopter blades. The spacecraft can fly, land, do a bunch of science, then take off again, fly around, scout for a new location, land again, and do more science. The spacecraft's the size of a small car, and it can fly several miles at a time. So Titan turns out to be the most optimal place to fly in the solar system. The atmosphere is dense and gravity is low, and this allows the Dragonfly mission to do science locally, like in direct contact with the surface, and then fly somewhere completely different geologically and do it again. So basically being able to sample a bunch of diverse locations over the surface. Dragonfly is slated to launch in 2027 and will take 9 years to fly to Titan, arriving in 2036. It's going to start its odyssey around Titan in a region near the equator that's filled with dunes made up of organic molecules. And then as the mission progresses, it will use what it has learned to figure out where to send the rotorcraft next. The data we get from this mission is going to revolutionize our understanding of prebiotic chemistry and the possibility of supporting life. So with that, I'll stop, but I want to mention that this is really just the tip of the iceberg of all the planetary research being done, all in order to better understand the conditions and processes happening right here on Earth. So I'll turn it back to you, Dr. Bennett.
Thank you very much. It's very exciting. I remember as a boy, I would look at books with pictures of planets, and they would all be very fuzzy. And now you've shown us these beautiful high-resolution pictures, and even more, you're studying the interiors of the planets that we can't even see. So it's very, very impressive. So now we're going to take questions that viewers have submitted, and I do want to remind the audience again that it's not too late to submit questions in the box below in the video on your screen. So there are already several questions here. Dr. Kalirai, you talked about the DART mission, and you mentioned a little bit about what comes after, but is there a specific DART-2 or next mission already in the pipeline, or what's coming next in terms of these future missions?
Yeah, so that's a great question. Thank you, Dr. Bennett. Yeah, there's a number of sequels in play here. So let's start by defining planetary defense, though. So NASA stood up a planetary defense office That office has actually a broader charter than just developing flight missions. So one of the goals is find all near-Earth objects, right? Our census right now is very incomplete, especially towards smaller objects. And so there's a number of facilities, including ground-based telescopes and future space-based telescopes, that'll be completing that census and finding all near-Earth objects. We also want to characterize them. We want to figure out what their shapes are, what their sizes are, what their orbits and trajectories are. So if one of them were to impact Earth, we could predict what's going to happen. And then the third step, which is the one that DART addresses, is to do something about it. So what are some of the other planetary defense programs in the international community? So one is a mission that the European Space Agency is developing right now called Hera. I believe it launches in 2024. Hera is actually a mission. It's kind of a 1-2 combination with DART. It's going to go back to the Dimorphos system, and it's going to explore the crater that the DART spacecraft creates on Dimorphos. It's going to orbit the system and characterize the impact. Another one that's being developed by NASA, by my colleagues at the Jet Propulsion Lab right now, is a mission called NEOSM, or the Near Earth Object Surveyor mission, which is going to be a telescope in space that completes this census of asteroids. And then two other quick points on that question is that NASA is a part of the decadal survey for planetary science, which is something that Dr. Riess alluded to earlier. As a part of that decadal survey, they've actually put planetary defense into the planetary science decadal survey. And so we'll have recommendations that come from the community that we'll be able to move forward on in the future. And then just very timely, in 2 weeks at APL, at the Johns Hopkins Applied Physics Lab, we'll actually be organizing an interagency planetary defense tabletop exercise where we bring together NASA, international space partners, FEMA, US Space Command, many other government organizations to simulate an asteroid strike. This is a blind experiment, so none of the participants know what's going to happen. There's going to be an asteroid strike of Earth that we're simulating, and we're gonna walk through the coordination that needs to occur among different government agencies to prepare and present a response to that impact. So it's a very rich field, and DART, the launch of DART has served as a spark for the overall planetary defense initiatives, and there's lots of exciting efforts underway.
Thank you very much. That's there is quite a bit going on, and that's encouraging. Let's see, Dr. Adam Riess, how much international cooperation versus international competition is there in civilian space exploration research, and what do you project will happen with the international aspects going into the future?
Right. Well, some of these missions I've been talking about, the James Webb Space Telescope in particular, or even Hubble before it, they're sort of too big for any one community or one agency to sort of swallow and deal with. And so generally they've been done in cooperation. In the case of the James Webb Space Telescope, it involves obviously NASA and ESA, the European Space Agency, and the Canadian Space Agency as well, generally partnering, building specific components and bringing them all together, a little bit like the International Space Station. And so that's been, I think, a very successful model. And looking ahead, the decadal survey that just came out recommended a very large optical telescope to launch in the 2030s or 2040s, a really massive telescope. And that will certainly require a similar level, I think, of cooperation. Space remains, I think, one of the best areas to cooperate because at its heart, all the communities themselves are very international and work together very well.
Okay, thanks very much. Dr. Sabine Stanley, what do you think might be the biggest misunderstanding amongst policymakers when it comes to civilian space research?
Great question. I'm not really sure that there are misunderstandings, but maybe I'll take this second to kind of highlight some of the things that are important to remember. First of all the science and the technology that makes the study of space possible is also the science that scientists use to study planet Earth, Earth's climate, and how the climate changes. So space scientists produce massive amounts of data. They can be used to study the Earth and really, really understand what is happening at a really fine scale and over time. Also, all of the resources that go into developing these space missions, they end up producing spin-off technologies that we use here on Earth. Everything from memory foam to cordless tools. to medical advances. So the science and the resources that go into the study of space benefit us here at home as well.
Thank you. Let's see. Maybe this would be good for Dr. Kalirai. Are there constraints on our supply chain that are now affecting the space industry?
Yeah, absolutely. It's a quite a serious issue, actually. We've seen a number of delays in even simple things like EEE parts that are common to the space industry, and given the impact of COVID as well as the slowdown of the supply chain, there's been delays in developing missions and instruments for space exploration due to that. The community is very adaptable and has learned quickly. And so for example, when you're starting new programs now in space exploration, given the lead times have gone up for those things, you're actually going in aggressively and purchasing a lot of the parts much earlier than you would have, say, 3 or 4 years ago, to try and minimize any schedule impact. There are also cost impacts, though, because the cost of producing the parts has gone up significantly since the time that you, for example, estimated how much your program is going to be. So, yeah, this has been a big issue recently, but it's been remarkable to see all of the launches over the last year, 2 years, despite some of these impacts and the hard work that the teams do to try and keep everything on track. But we are actively trying to stay ahead of it by purchasing things earlier in the process.
Makes sense. Thanks very much. Dr. Riess, you mentioned the Hubble, the Webb, and the Nancy Grace Roman telescope. One of the questions here is how do these interplay with each other? How do they connect in terms of you as an observer?
Yeah, that's a great question. And the answer is they're very complementary. And the reason is because they're very well thought out, as I described, by this decadal process that thinks about the needs. Generally, to study space, it's not sort of one kind of instrument we use. It's very interdisciplinary, very interwavelength. And sometimes we need a wide angle to look for rare objects, which is what Nancy Grace Roman can do. Just like on a backyard telescope, you have the viewfinder that allows you to sort of look broadly. Then you might have something that goes deep and studies like the James Webb Space Telescope. And then, of course, sometimes we observe at blue wavelengths, which is Hubble is very good at. Sometimes we have to observe very distant objects. The expansion of the universe has shifted most of the light to the red, in which case we need something like the James Webb Space Telescope, or to see through dust. So, it really depends on the application. In some ways, we're sort of like Batman with our utility belts. We need, different tools for different situations to grapple with things. And we figure out whichever telescope we need at that time, even using them sometimes in tandem.
Right. Thanks a lot. I have a question here. I think I'll give it to Dr. Sabine Stanley, although I know this is not your area of expertise. But what are some of the biggest challenges to human exploration of these planets in the solar system?
Yeah, that's a great question. So there are lots of challenges, but I think I'll highlight one that people don't always talk about or always think about, and it kind of gets to what Jason was talking about earlier. If we're sending humans into space, they are not going to be protected by the magnetic shielding that we have here on Earth from harmful radiation, high energy particles that are coming from the sun. So if you're thinking about sending humans to Mars, for example, you're spending an extended amount of time unprotected from these radiation environments. And we need to figure out how to protect humans in that so that they can survive a longer trip and do what they need to do there. The problem is that most of the ways to protect things like this are heavy. So shielding with some sort of lead shielding or something like that, anything that's heavy is really hard to launch off the surface of the Earth. So you get more and more expensive the more you think about having to do this. So I'll highlight that as one of the biggest challenges that needs a lot of work.
Great, thanks. And I totally agree with that assessment too.
Dr. Bennett, can I add one to that list?
Sure. Yeah.
So, one of the biggest project at NASA right now is something called the Artemis program, which aims to return the first woman and the next man to the surface of the moon in the next few years, right, in this decade. But one of the key differences between Artemis and Apollo is that we want to go back to the moon to stay instead of just coming back. And so how do you achieve that? This is a big challenge for human exploration. So, for example, when the astronauts of Apollo went to the moon, one of the surprises was how harmful the dust on the moon can be in terms of the impact that it has on spacesuits and shielding and things like that. Going forward, we're going to want to know, how do we bring power to the moon surface? How do we excavate the moon surface? How do we communicate from the moon surface? How do we do in situ resource utilization and use the natural resources of the moon to develop oxygen and water and other things that we're going to need to establish that sustained presence. So the technology development that has to happen, bringing together industry and not-for-profits and universities and in partnership with the goals of the Artemis program is also a huge challenge.
Thank you. Let's see, there was actually a follow-up for you here, Dr. Kalirai, on what is the time frame between detecting an object that might be on an Earth impact course and actually launching something to move it and having it get there?
Yeah, so that's a hard one to answer. It depends on a lot of specifics. But if you just back up a minute, remember, so the Earth is not stationary, and there's an asteroid coming towards us, right? So we're going around the sun, and there might be an asteroid coming here, and all we're trying to do is nudge that asteroid a little bit and slow it down so that the Earth gets out of the way as it's going around the sun. It moves a little bit out of the way, and the asteroid just flies by, right? That's the goal. So how far out is the asteroid at the time that you detect it? What's the probability that it's going to hit us? How large is the asteroid? You're going to want to understand all of those problems before you develop a specific solution to that threat. So you probably need a range of different technologies that are ready to go. And so DART is kind of the brute force technique, right? Build a giant spacecraft and collide it into the asteroid and move the asteroid. And so maybe we want some DART spacecrafts that are ready to go or almost ready to go, and we could quickly adapt them for that specific situation. But not all asteroids will probably react to a kinetic impact the same way, depending on whether it's a rubble pile or what material it's made out of, or if you impact a crater or something else, the shape of the asteroid, how fast it's rotating, etc. And so there's probably other technologies that we'll want to develop, and then depending on early characterization of the object that's headed towards us, you identify the right technology.
Great, thank you very much. Dr. Adam Riess, will the Webb Space Telescope be able to see black holes or even inside black holes?
Oh, wow. Well, that's a really good question. It's, as the name sounds like, it's difficult to see black holes. There are various indirect means that we have of detecting black holes. Probably, and people may have seen this in the news in the last couple of years, a new capability for sort of seeing black holes is to use radio telescopes spread throughout the entire globe, acting together like one giant telescope process called interferometry. And you actually, believe it or not, get the highest resolution if you could observe in radio wavelengths with that technology. And that technology has actually been used to see the first black hole in the center of a galaxy, and is being used to see the black hole in the center of our galaxy. So probably more the expertise of radio telescopes spread over the world than the James Webb.
Thanks. There's a question. I may admit Dr. Stanley, but then Dr. Kalirai may want to chime in also. But what does the future workforce of the space industry look like? And how does STEM education play a role to grow a stronger U.S. workforce?
Yeah, thanks. I can start with that. I'll say that the future workforce of the space industry has to become much more diverse than it is right now. We need to make sure that we have the best talent, the best ideas, the most creative people. And you can only do that if you include everyone, if everyone has the opportunities and is not kind of hindered from doing this work. Most of work in space is done on teams. Teams function better the more diverse they are. There's research for that. So we need to work on such a way so that we can make sure that everyone who's able and willing and interested in doing this can do it. And of course, STEM education is huge for this. We need folks that are skilled in the quantitative side, skilled in the computational side, skilled in building and engineering. But we also need people who are skilled in communicating the science and in understanding how people work. I think that's a huge thing. Social sciences is going to be huge to complement the STEM workforce in the future to advance the space industry. Dr. Kalirai, I don't know if you want to add anything to that.
I agree with everything that you said. I mean, I think the inspirational part is going to be very important as well. Many of us became interested in space as young people because of things that NASA was doing and other things that we saw. The space industry is changing very, very rapidly, right? There are hundreds of new companies coming and getting involved in the space. So, you couldn't imagine a more exciting time for students to get involved in different sets of opportunities that just simply didn't exist 10 or 20 years ago. The other thing that I think is going to be very important is that we've touched on a few projects in this brief, but there's a number of large scale survey type programs that are coming online as well. Dr. Riess highlighted one of them with the Nancy Grace Roman telescope. There's another one, the Vera Rubin telescope on the ground, which is going to be surveying 18,000 square degrees of the sky every 3 days and creating just a treasure trove of data, and almost like building this movie of how things change over time in the universe, and mining that data and finding new discoveries is going to be very important. And so I think there's ample opportunity to both grow partnerships and internships in the emerging and burgeoning space industry, but also working on some of our data analytics and machine learning and data mining capabilities that allow us to dig nuggets out from these massive data sets that are coming down the pike.
Dr. Riess, you referred before to the kind of the international nature of the science and the space missions, kind of in a more concrete way, down to earth on a day-to-day basis. How do scientists get together and decide what they want to work on together? How do they choose? What's the process where that happens?
Right. Well, teams form often organically, or they might form, to tackle a very big problem. And communication is facilitated, like everything else, over the internet, over conferences and gatherings. And then generally it starts with a proposal. It generally starts with a proposal to maybe get time on the James Webb Space Telescope, maybe for funding, anything like that. It's, people who are attracted to a similar problem. Maybe once the team is organized, they seek additional capabilities that they don't have. But the international community has sort of worked that way for a very long time. And I think space, almost more than any other area, benefits from that kind of work.
Okay, thanks. This is probably best for Dr. Kalirai, but what about space junk? Is it a problem? How big a problem is it? You have a way of cleaning it all up?
Well, the best way to clean it up is to not make it in the first place, right? So, I mean, I mentioned the rapidly growing number of satellites. And so you might think, okay, well, if there's going to be 100,000 satellites up there in 10 years, there's going to be this huge amount of space junk. But no, not necessarily. I mean, we need to develop and launch these new satellites with a plan to either shoot them up into a higher orbit so they're not, at the end of their life, they're not in a low Earth orbit creating space junk, or have them burn up in the atmosphere as a part of a descent program. So it is a serious threat. We don't have, like right now, there is no air traffic management in space, right? We don't have any regulations or norms for launching satellites. And so we do need to put some rules in place. But at the same time, I think all of the satellite providers need to be very responsible in mitigating future space junk.
Okay, thanks very much. I guess there is a question here about the Don't Look Up movie. And I've had a lot of people ask me, is this really, how plausible is this? So I think I'll put that to Dr. Riess, who is an avid moviegoer.
Me? Okay.
Yeah.
Interestingly, in terms of plausibility, the research that the main character is actually doing is very similar to the research that I do, which is to take wide area images with telescopes and look for exploding stars called supernovae. Although sometimes along the way you find something moving, which turns out to be an asteroid. And Dr. Kalirai described, all the kinds of efforts one could go through, I think proactively, to try to steer or move or blow up or disintegrate, something like that coming. So I would say, you know, the basic building blocks of the science fiction movie plot seem very plausible. But then, of course, it goes kind of, I would say, you know, gets off the rails and makes a lot of fun of current circumstance. And, you know, who knows? I'm, as a scientist, can't say anything really about how realistic those actions are.
Thanks. There's a couple of questions here related to the future. They're a little bit different, but let me just put them together. So one says, in your mind, what does space exploration look like in 2032? And do you think public-private partnerships will increase? And then there's another question of what are you most looking forward to in this field? And what I'd like to do is go to all three of you about these. Dr. Stanley, would you like to pick on something there?
Sure. So in terms of 2032 and public-private partnerships, I think it's important to realize that space exploration has always been a public-private partnership from the very beginning. NASA has always worked with private industries to develop the technology that's needed to do this. And so I think that's obviously going to continue. And as we're seeing more trends of having private industry supply things like launch vehicles and things like this. 2032 also, I know that sounds far away, but from the planetary science world, that's like tomorrow. We've already got plans for what's happening in 2032. And that's really because designing missions and planning for missions, they take time, and you really have to have a good plan well ahead of time. So we know what we want to do, and we know what missions are in the works, where they're going, and what science we're going to learn from those in 2032. I think I am really looking forward to JWST. I think there's a lot of science being done with JWST. One thing that hasn't really been discussed a lot is JWST is also going to tell us about our solar system. We're going to learn things, for example, about the ice giants Uranus and Neptune, places that haven't been visited since the Voyager 2 mission in the early 80s, late 70s, early 80s. So I'm really excited to get the level of detail of information we are about our solar system from JWST.
One of the other, does somebody else want to comment on?
Sure, I can. I'm also very excited about JWST, especially because it's almost here. I mean, it's up there. We're just focusing it. Can't wait. But a little longer term, an area that I think has tremendous discovery potential for space exploration is the new capability just developed in the last few years to look at gravitational waves. Gravitational waves are ripples in space-time as a result of very heavy, massive objects moving in space, in many cases dark, like two black holes spinning into each other. This has given us a kind of new window onto the processes that go on in the universe. And it's just getting going, and I can't wait to see what we learn from that.
I can weigh in as well. So in terms of what does space exploration look like 2032, I agree with Dr. Stanley's answer very much. We get ahead and try and develop these missions well in advance, and sometimes they can take a decade or longer to develop. I think one of the new opportunities is, as a space scientist, I have a bias that I'm always coming at problems from a science first perspective, trying to identify the science that you want to go after, and then you build technologies and an architecture to close that science. I think as we move forward and you see this rapid growth in the space industry, you can actually turn that problem around a little bit. So, when you have 100,000 satellites, what sensors, what instruments can you put on these satellites to close a science problem that you wouldn't even have known to ask before you had that space industry? So I think there's some opportunities to think more creatively about the kind of science that we're doing. Public-private partnerships, Dr. Stanley nailed it. We've been doing it for a long time. We just launched the DART mission, a NASA mission that launched on a SpaceX rocket, a private company. So we do this all the time. And, I was fortunate enough to stand next to the launch pad where DART launched from on the day that it launched. And the booster for the rocket had flown multiple times in space. And they had another booster sitting there that has flown 11 times in space. So it's remarkable what private industry has been able to do in terms of recycling these vehicles, just like we do with airplanes. We don't fly them once and then ditch them, or cars, right? We fly them back and forth. We're doing the same thing with rockets right now, and it's driven the cost to launch and therefore enable space exploration down a lot. And then with respect to what I'm most looking forward to in the future, I would say the search for life, right? Dr. Stanley highlighted this exotic world in our solar system, Titan, that's very similar to Earth, and we're going to explore it. There's lots of other worlds in our solar system that have oceans, have water, and wherever we look in our ocean, bottom of the ocean floor, intense pressure, no sunlight, life is thriving. And so could there be life right in our backyard in our own ocean? Let's go explore Enceladus. Let's go explore Triton. Let's go explore these ocean worlds.
Great, thanks very much. I think we're probably don't have time to squeeze another question in, although there are some other interesting ones here. Maybe we'll have to come back and do this another time. But for now, I would like to thank the panelists, Dr. Jason Kalirai, Dr. Adam Riess, and Dr. Sabine Stanley for joining me here today. And of course, a big thank you to everybody who has attended this briefing and to those who submitted these questions for our experts. A recording of this event will be made available on this website, which is the online home of the Johns Hopkins Congressional Briefing series. More information about Space at Hopkins can be found on our website, and to learn more about APL's civil space work, you can also visit that program's website, which is being shown on the screen. We're happy to entertain questions, not just in the briefing, but anytime. So thank you very much for joining us and discussing the excitement that we all feel about the space efforts, both now and in the future. Thank you.